This program is a presentation of UCTV for educational and non-commercial use only.
Researching the geophysical history of the Gulf of California. Explore the largest shake table in North America. But first, high-tech archaeology helps verify ancient historical texts, all in this edition of On Beyond.
Sacred texts are fundamental to the lives of billions of people around the world. Very little of biblical history as depicted in the Old Testament or Hebrew Bible has been verified through the archaeological record. Yet it's precisely this opportunity that exists as archaeologists armed with new digital technologies try to establish synchronisms, references in a sacred text that parallel historical accounts as reflected in artifacts, inscriptions, and other parts of the archaeological record. Case in point, historical evidence of King Solomon is scarce. Excavations at Hatzor, Megiddo, and Gezer have uncovered structures that some archaeologists date to Solomon's reign. But that conclusion is not definitive because it is believed these sites were later destroyed by an invasionary force of Egyptian pharaoh Shishak I.
While scholars argue about the exact year and the precise routes that Shishak's forces took, they agree that the military campaign took place during the 10th century BCE, the most hotly debated period in biblical archaeology today.
The most detailed evidence of Shishak's attacks across Palestine is visible on the excavated ruins of the great temple of Amun at Karnak in the ancient city of Thebes, modern-day Luxor in Egypt. Here on an outer wall is a monument to Shishak and his victories. Depicting the pharaoh himself, the carved stones today feature roughly 80 name rings of towns and settlements of what appear to have been at one time as many as 180 rings. Most researchers now agree that this relief scene represents a topographical list, with each ring the name of a place subjugated by Shishak or his forces, commemorating his invasion of Palestine in the early 10th century BCE. The Palestinian topographical names still preserved in Karnak include a number of well-known current sites: Gaza, Gezer, Tirzah, Jezreel, and Megiddo in the north. As such, this facade is a treasure trove, helping archaeologists understand the impact of the Egyptian state on societies in the southern Levant nearly 1,000 years before Christianity and over 1,600 years before Islam was born. As part of their effort to develop a digital archaeology atlas of the Holy Land, researchers at UC San Diego's Center of Interdisciplinary Science for Art, Architecture, and Archaeology are using the latest archaeological data mining and visualization tools to postulate the direction and significance of Shishak's campaign based on the name rings at Karnak and the findings at excavated sites in Israel and Jordan with layers dating back to the biblical period. The story begins here in Tanis on the Nile Delta. This temple town was home to Shishak and successor pharaohs of Egypt's 22nd dynasty and remained so for roughly 200 years. As reconstructed by Egyptologist Kenneth Kitchen, the pharaoh probably led the advance along the Via Maris, the Way of the Sea, all the way to Gaza along the North Sinai coast.
Before spearheading his main forces' advance north to Megiddo, the pharaoh had dispatched at least 3 large task forces, or as Professor Kitchen called them, flying columns, to the south of the country to subdue fortified sites in the Negev Desert and the Wadi Araba Rift Valley that separates modern Israel and Jordan.
The archaeological record, including recent finds by researchers from the University of California, San Diego, and Jordan's Department of Antiquities, provides major clues to the route taken by forces along the middle prong of the northern Negev offensive. The force swept eastward to Sharuhen, a community listed on the temple at Karnak. From there, the Egyptians followed the Wadi Gaza east to the fortress town of Beersheba. then on to Malhata and Arad. There is evidence the force continued on to attack the fortress at Hatzeva, some 50 kilometers south of the Dead Sea, a critical outpost because it permitted control of the overland Arabian trade route, including the copper trade with Edom, located across the Wadi Araba Valley. It is there, traveling east from Hatzeva, just 18 kilometers, that UC San Diego archaeologist Tom Levy and Jordanian archaeologist Dr. Mohammed Najjar are excavating Khirbat en Nahas, a site rich in copper ore in Jordan's Feinan region, the biblical Edom. The excavations have unearthed the largest Iron Age copper production center in the southern Levant. More than 24 acres in size, the site is covered in thousands of tons of ancient black metallurgical slag.
To our surprise, high-precision radiocarbon dating at Khirbat en Nahas show that copper metal production was carried out some 200 to 300 years earlier than scholars believed until recently.
This brings the occupation of the site into the orbit of the 10th and 9th centuries BCE, the time of David, Solomon, Rehoboam, Jeroboam, and Shishak. Recent finds of Egyptian artifacts at Khirbat en Nahas lend credence to the excavators' new theory that the massive copper production center may have been a target of Shishak's army, given that Khirbat en Nahas is just a day's journey from Hatzeva, one of the neighboring sites probably destroyed by Shishak. To ensure the most accurate data collection, UC San Diego archaeologists record all data in 3D, with X, Y, and Z coordinates. Z is for elevation, collected with total stations and global positioning systems.
This enables researchers to control precisely the spatial location of architecture, artifacts, and other discoveries. We've created one of the first completely digital-based recording systems for archaeological research.
Digital photographs are taken of ancient buildings discovered in an excavation, for instance, and downloaded into the computer where they can be accurately drawn with a Geographic Information System, or GIS. Researchers can then reconstruct the site on their laptop computers in the field on a daily basis or back at home in California. The UCSD Center is using digital tools to analyze all sorts of data, from regional settlement patterns to small artifacts. The new excavations at Khirbat en Nahas are providing exciting new data for examining theories concerning the role of metal production on the rise of the biblical kingdom of Edom, as well as Shishak's campaign. Excavating a 6-meter deep mound of ancient metallurgical debris in Area M at the site, that's over 20 feet deep, UCSD and Jordanian archaeologists for the first time have exposed a complete record of Iron Age metal production in the region.
During the course of our excavations in the Area M building, several Egyptian artifacts were discovered on the floor that may relate to Shishak's campaign or trade between Jordan and Egypt around that time.
These include a scarab originating from the eastern delta in Egypt, possibly from Tanis, where they may have been produced during the reign of Shishak and his predecessor in the early to mid-10th century BCE. Another important find, an Aegis amulet made of faience. Such amulets are primarily linked to the goddess Mut, and since there was a Mut temple in Pharaoh Shishak's capital city of Tanis, this amulet may also have originated from this region. These artifacts clearly place the building at Khirbat en Nahas in the time frame and historical context of Shishak's three-pronged attack across the Negev.
We excavated the large slag mound at Khirbat en Nahas, presumably slag and other debris from the copper factory, and pinpointed the location of 22 radiocarbon samples. Those samples were then dated at the Oxford Radiocarbon Accelerator Unit by Doctors Tom Hyam and Christopher Bronk Ramsey.
The excavations in the slag mound revealed only 3 major strata through this massive accumulation of ancient metallurgical debris. By applying Bayesian statistics to the calibrated radiocarbon dates, it is possible to model the sequence of events in this part of the site. The highest probability for the earliest point in time when smelting may have been carried out at this earliest location, stratum 3, is put at 950 BCE. Stratum 3 itself spans between 5 and 135 years, with a highest probability associated with a briefer period of only 40 years.
In these early phases at the site, over 3 meters of metallurgical smelting debris may have been deposited in less than 50 years.
At the end of Stratum 3, the slag mound was truncated and the 4-room building was constructed in Stratum 2. This period dates from as early as 910 to as late as 800 BCE, with the highest probability that the end of the Stratum 2 occupation in this area came in 840 BCE. In other words, the excavations at Hibad and Nahas show that there was a major disruption of the early 10th century BCE copper industry at the site between Stratum 3 and Stratum 2, around shortly before 910 BCE. This raises the tantalizing question, could this disruption be related to the military campaign of Shishak's troops that crossed the Negev desert into the Wadi Araba Valley? The force reached Hatseva, and it was only a day's journey further east to the metal production center at Hibad and Nahas. The period of disruption in metal production appears to coincide with Shishak's reign from circa 945 to 924 BCE, and it is consistent with the 5th year of the reign of Judah's king Rehoboam, 926 BCE, when most scholars believe Shishak's military campaign in Palestine began. Prior to the excavations by UC San Diego and Jordanian archaeologists in the Feinan district, researchers assume that the Iron Age only began in this part of Jordan in the 6th or at the earliest 7th century BCE. This was based on the fact that most Iron Age excavations had taken place at sites on the highlands of Edom. Sites such as Busera assumed capital of biblical Edom, and no evidence of occupation in the 10th or 9th century BCE had been found there. As a result, it has been believed that activities mentioned in the Bible of David, Solomon, Hadad, son of the king of Edom, or even Pharaoh Shishak, regarding the early Iron Age history of Edom, might be pure myth.
Those assumptions ignored the important copper ore district of Feinan in the lowlands of Edom. Now, thanks to a mix of traditional and digital archaeology methods and high-precision radiocarbon dating, we can refute the earlier assumptions.
And by tracking the archaeological evidence of Shishak's military campaigns north to Megiddo and east to Hatseva, and using it as a touchstone for analyzing the biblical citations about Shishak, a new understanding emerges about this period and the role Shishak may have played in the disruption or even devastation of the largest known Iron Age copper factory in the eastern Mediterranean. As such, the story of Shishak's campaign in Palestine underscores the need for more interdisciplinary science and technology-based research in the investigation of the relationship between the Bible and history, indeed between all sacred texts and the archaeological record.
Baja California was part of mainland Mexico until about 10 million years ago. Opposing forces between the North American and Pacific tectonic plates caused the peninsula to break away on a slow-motion journey away from the mainland. Today, spreading centers along the seafloor are widening the Gulf at the same time that the drifting plates are pushing Baja California cities like Ensenada on a northwesterly route away from the Mexican mainland. The new ocean being born in the Gulf will add to what is currently a shrinking Pacific Ocean. Geologists from Scripps Institution of Oceanography at UC San Diego are using remotely operated vehicles to excavate rocks from deep-sea canyons to map the expanding ocean bottom and document the birth of the next ocean basin.
We want to study the structure, the forces that initiated the rupturing. We want to study magnetism. We want to study the transition from continent to a full ocean basin. And the Gulf of California really captures the initiation from continent to a young ocean basin. Okay, it's not really an ocean, it's still a sea right now, elongated sea. But pretty soon, well, geologically speaking, it will become an ocean.
In May 2008, Scripps marine geologist Peter Lonsdale led a month-long expedition to the region. ROV Jason plunged hundreds of feet to the muddy bottom to help researchers collect large chunks of rocks from deep-sea cliffs and outcrops in specific locations along the seafloor.
Previously, hydrothermal vents in the Gulf had only been found in Guaymas Basin, and we found hydrothermal vents in Carmen Basin and Saucipuedes Basin and multiple basins, and so this has never been discovered before. And a few of them actually had the shimmering water pouring out of it, the superheated water that was actually being ejected out of the seafloor.
A magma is a molten hot body, and some of them don't make it to the surface because there's a lot of, for example, in the Gulf of California, there's a lot of thick sediment cover on top. And so this hot body underneath thick pile of sediments will still be hot, and then the water, which is cold from the Gulf, will penetrate and then will be heated and come up. So that's what we call the hydrothermal system. And as the water gets heated up, it picks up, for example, copper or gold and silver from the rocks. It interacts, this water, and then it will deposit when it becomes colder. So that's how some of the economic mineral deposits that we mine right now are being performed. So these hydrothermal activities will leach the minerals from one place and deposit it, concentrate in another place. So that's why, continental margins, because right now the Gulf of California is still narrow. So both sides are still continental margins. Baja side and the Mexican side are still margins. And these hydrothermal activities are concentrating economic mineral deposits.
In my research, this tells me that there's, this hydrothermal system caused by intrusions is actually happening. These magma being injected into the sediments, heating it up and driving out the water, evidence being these vents.
It will take a few million years before the new basin forms. Geologists are still unsure what it will look like, or if there are yet unknown tectonic forces that will interrupt its formation. Scripps scientists are preparing future expeditions to sample more rocks along deep-sea cliffs in order to learn more about the new ocean forming below the Gulf of California seafloor.
In late June, we're going back out to sea with a professor at SESESI, and we're going to be doing a geophysical cruise, seismic profiling, trying to image these igneous structures in 3 dimensions instead of just in 2 dimensions, so we can understand how they interact, not in a 2D, but actually in a 3D realm. And then in October, I'm leading a cruise in the southwestern part of the Gulf, where we're going to be doing additional rock sampling where we didn't go with Jason. And this is correlating to my seismic profiles as well, so we can see actually what's going on there. Are these, volcanics? Is it continental crust? Where's the boundary between oceanic and continental crust? So hopefully we'll be able to answer those sort of questions.
This has been a presentation of Scripps Institution of Oceanography at UC San Diego. Visit us online at scripps.ucsd.edu.
Earthquake. Devastating to lives and the economy, and one of the hazards of life in California. For over 15 years, UC San Diego has led in seismic design research with its large-scale test facilities and unparalleled faculty. One of those facilities is the largest of its kind in North America, the UCSD NEES Shake Table at UC San Diego's Jacobs School of Engineering's Engelkirk Structural Engineering Center. Operated as part of a national collaboratory called NEES, the facility provides unique capacities and opportunities for seismic engineering.
Behind us, we have what we call the NEES UCSD Shake Table. NEES stands for Network of Earthquake Engineering Simulation, and is located at UC San Diego.
NEES is it's an operating company, the actual organization. It stands for the Network for Earthquake Engineering Simulation. We are funded by the National Science Foundation. We operate 15 different equipment sites around the country, which are all linked by information technology capabilities. The goal being that we test large-scale structures, geotechnical specimens, and tsunami specimens in one of our sites to examine earthquake performance of these systems. This is a new approach to research in that it's collaborative, It's shared use facilities, so I can go in and use the equipment at the University of Minnesota as if it's equipment in my own laboratory. So we eliminate a lot of the resource problems that typical universities have where they don't have the right equipment to run the tests that they need. It allows researchers around the country, principally university faculty, to do more involved, more complicated, more realistic kinds of testing so that the country can benefit from improved knowledge about how different systems, buildings, bridges, dams, different kinds of systems perform under an earthquake or other kind of extreme loading.
This is the largest shaking table in the United States, and as you can see, it's an outdoor environment. Being outdoor has the advantage that we don't have the space limitations in many other shaking tables that we see in the United States or abroad. This shake table has been designed for different scenarios. The table can hold 2,000 tons. So if we put it in terms of how many cars or so, it will be of the order of 1,000 cars piled one on top of the other, 1,000 trucks. That's the biggest size. That's the structure we have at the back here. Weighs of the order of 400 tons, so we can still place 5 times more weight than expected. Why do we do this? Maybe that we don't test a building structure that is somewhat light, but we may want to test soil structures. Let's say we want to take very large soil containment structures like retaining walls. They are very heavy, and the table is geared for this case.
To move things of such massive scale requires some unique equipment.
We have some gigantic, very high performance actuators. These actuators can drive the table at about 6 feet per second, or 1.8 meters per second. They have a force capacity, combined force capacity of 700 tons. And they have a stroke of plus or minus 26 inches. In terms of power, may be equivalent to what is spent in one night by a neighborhood between 5,000 to 10,000 people in one night, and we spend that in 45 minutes. Now, we cannot draw all that power directly from the grid because we create a huge problem, and we can do is we just take a little bit at a time and store it as potential energy. We just, like if we are inflating a balloon very slowly, and we we inflate the balloon and then we let go, and the energy goes into the actuators.
The balloon Jose refers to is actually an array of huge pressure accumulators. You can think of them as giant compressed air tanks, except in this case, oil is pressurized in the tanks. That pressure is stored energy, the energy that will drive the table's actuators. The accumulators are connected to the actuators through a serpentine network of high-pressure feed and return piping. The actuators that move the table are essentially giant piston jacks, very special jacks, that can be precisely controlled. With one actuator at each end of the table, they push in unison to recreate ground motions of a seismic event. During a test, all the weight on the table, up to 2,000 tons, actually floats on a thin film of high-pressure oil in the hydrostatic bearings that support the table. For a typical test project, large-scale test specimens, sometimes entire buildings, are constructed directly on the shake table. Instruments are installed to observe many parameters on the specimen, from displacement and acceleration to deformation among the specimen's components. All the table's actions are precisely controlled by computers from the shake table's control room. From here, technicians can deftly move an entire building as they wish, allowing them to achieve the exact specifications of a test's seismic record. This gives them the unique ability to perform real-time tests, actually recreating the motions of an earthquake. When a test is initiated, the actuators drive the table back and forth, and the specimen, attached to the table, is subjected to ground displacement, much like that which occurs during an earthquake. Recently, the facility subjected the most massive structure ever tested to the most extreme seismic record ever used, the 1989 Loma Prieta earthquake. The resulting test not only clearly demonstrated the facility's effectiveness, but the spectacular nature of these tests.
4, 3, 2, 1, running.
The test sequence not only shows the dramatic nature of the test, but how the test specimen is a tool that allows researchers to observe the behavior of different structural elements. It reveals the movement of concrete columns, the actions of walls as they transfer shear forces, the drift or displacement between different levels, the lateral movement of floors and their behavior. And in the end, the structure stands, surviving one of the most severe seismic events recorded. Combined with volumes of instrument data, the researchers have much to work with. This and other watershed tests on the shake table prove once again that the NEES Ucsd collaboration continues to provide invaluable tools for science to advance our knowledge of how to build things better.